Hello and welcome to week 3. This week we will be cleaning data using Python. This week we'll be talking about the goals of data cleaning, how to detect data quality issues, using Python to clean text, and using Python to convert what we know to be numeric data into numeric data that we can use in Python. So what are the motivations behind data cleaning? Well, as you'll find as you advance in your data science career, you'll find that not all the data you come across is ready for running in a regression. Perhaps you have very wide data frames where you have a different column for each province's data. Or perhaps you have files where there might be placeholder values that we need to clean up. Maybe you're importing files from a different country or a different locale that might have a different decimal format. In some cases, we may need to clean data files before we're able to use them in Python. In my professional experience, I found that this is the most time-consuming part of our analysis. It's also one of the most important, because if we give the computer garbage to chew on, all it's going to give us on the other end is fancy garbage. Our goals of data cleaning are to detect outlier readings. So are there any data points that would, on their own, significantly influence our final result? We also want to find any values that are not numbers and convert them into something meaningful so that they don't interfere with our analysis. For example, we may want to convert missing values into something that's known as not a number. Values that are in text format that have commas in them, for example, we can infer that 5,234 in North America could be interpreted as 5,234, but perhaps in a different locale, that might be interpreted as 5,234. So part of our data cleaning is to make sure that our numbers are in the correct format. We may need to find sentinel or placeholder values and convert those into numeric values we can work with. As part of the data cleaning process, we want to use this to make sure that if we have a data dictionary that ships with our data set, that the values that we find in our data matches what we expect to find from our data dictionary. And finally, we'll use data cleaning to get rid of columns that we don't need in our analysis, or to get rid of extra rows that might be read in as metadata or data about our data. I want to stress an important point about the data cleaning process. We're going to define clean data as data that can be read and processed by our computer. We are not talking about whether the data is accurate, only whether it can be processed by the computer. In other words, can we give this cleaned file to the computer and have it give us a result on the other end? Remember, computers can only give you a result, and the result that they give you is only as accurate as the input data that you give to the computer. If you give the computer inaccurate data, the result is not going to be accurate. When we talk about clean data, all we're talking about is data that can be read and processed by a computer. So let's get into our first data cleaning. We'll be working with some cooperative education salary data. So you have been given a data file which contains the salary data for cooperative education or co-op students at the University of Waterloo. In this data file, we have a list of programs, their work term level, and average salary at that work term level for the given program. Is there a link between work experience and salary? Let's quickly review our analysis steps. We're going to read in our CSV file into Python. We're going to clean our data. We're going to skip over step 3. There's no need to join with other data files. We're going to see if there are any correlations between our variables, and then we will build a regression to see if we can support or refute our null hypothesis. Let's take a quick look at the data. You'll find the data in Co-op Salary 2019.csv, and this will list the average earnings by hour by program and work term for University of Waterloo students for the winter 2019 term. Let's take a look at that file in Python. We have 3 columns: program, term, and salary. So for example, our first row for Applied Health Sciences, in work term 1, the average co-op student earned $15.90 per hour. For arts, a first-term student earned $17.59 per hour on average. Now, those who have already looked at this file, or on first glance, you might see we have a few data issues, but we'll get to those in a minute. Let's talk about our null hypothesis. How are we going to either prove or refute a link between work experience, the work term level, and salary? So when we build our model, we need to think about a hypothesis that we can falsify. We're going to build evidence to reject our null hypothesis so that we can accept our alternative hypothesis. Our null hypothesis is that there is no correlation, there's no association between work experience and salary among co-op students. This is what we're going to attempt to prove false. Our alternative is that if we prove that no link exists between work experience and salary, if we can prove that false, then we can accept the alternative, which is there is an association between work experience and salary among co-op students. We're going to reject our null hypothesis if our coefficients p-values are 5% or better. So we're looking for 0.05 or less when we run our regression. So how can we detect data issues? Well, first, we can eyeball the file, open it up in Spyder, Notepad, TextEdit, and take a quick look. This can be useful for small files or perhaps very obvious issues, for example, extra rows at the beginning or the end of a file. What I've found in the course of my work is once you get beyond about 50 to 100 rows in a file, that's a little bit too big to be eyeballed. As an alternative, we can read our file into Python and just start poking around with a few built-in functions. We can get the columns for our data frame. We can use the describe function to get a statistical summary of our data frame. We looked at this in week 2. We can get a list of unique values in a column of a data frame using unique, and we can use a special function called dtypes, which will tell us what kind of data we're holding inside of a column in our data frame. Let's quickly flip back to our file and just remind ourselves of what we're looking at. So again, we have 3 columns: program, term, salary. If you would like, pause the video for a moment and jot down the first few items that come to mind regarding data quality. Are there any issues that you can see on screen right now that might interfere with our analysis? Go ahead, pause the video, make some notes. All right, let's take a look at some of the issues that might come to mind. If we look at Applied Health Sciences, we see that the 6th term has a dash. If we look at the program column, we see that the first 3 rows of architecture seem to be ARCH, and the last 3 rows are the full word architecture. We see the dash in arts as well. And if you open the file on your local computer, you might see that we have a few other programs that have dashes for the average hourly salary for the later work terms. So how could we find some of these issues using Python? Well, remember, we can get details about our data frame by using the describe function. Remember, this will give us a data frame that gives us the percentiles where data occurs, min, max, and mean for any numeric data, our sample standard deviation, and our count of values. And if we want to get our description, we do we create a new variable, say call it description, set it equal to SalaryData.describe. Let's give that a try now, shall we? So I'm going to come back into Python here, and I'll start writing the code to read this CSV into our environment. So I'm going to create a new variable called SalaryData, and I'll set this to pd.read_CSV, and we'll read our co-op salary 2019 CSV file. If I go back to my Variable Explorer tab, I now have a variable called SalaryData, and it holds my 3 columns: program, term, salary. Now you might also notice this is another method of data exploration. When I bring up the SalaryData data frame in my Variable Explorer, notice how the term column is highlighted, but the salary column is not. This is a clue, also known as foreshadowing. We may have a problem here. But let's first get a description of our data frame. I'm going to create a new variable called description and set this equal to SalaryData.describe. And if I run all of this, I now have a new variable called description with my column name, with only one column actually this time, term. I've got 54 values. The average is 3.5, and standard deviation in this case doesn't have much meaning. My min value is 1 and my max value is 6. So my work terms range from 1 to 6. Now, here's something interesting. Notice that I did not get a description for salary. I did not get a description for salary. So that is a hint to us already that salary might not be in a numeric format. So only one column was described in our previous example. Now we can have columns that have non-numeric data in them, and we can detect this using the dtypes attribute on our data frame. This will give us a list of all the different data types we're holding inside of our data frame. So let's check it out. Let's see what kind of data types we're dealing with. I'm going to print out my SalaryData.dtypes. And I see here I've got program is an object dtype, my term is an int64, and my salary is an object. Now, what is an int64? We covered this previously. But an int64 is a whole non-decimal number. So 1, 3, 5 are examples of integers. So term has been read in as a numeric type. Salary, however, has not. It's got this type object. Object is kind of the catch-all bucket that pandas and Python will throw data into if it can't figure out if your data is numeric. Now, we're not limited to using describe on just number data. We can also ask describe to describe our non-numeric columns to us. Now, because they're non-numeric, we won't get values about their mean and their standard deviation, but we'll get an idea of what values we have. For example, the unique count of values, the count of values, so the total number of rows, the top recurring value, and the number of occurrences. In order to get this description, we need to use the optional include parameter and specify that we want all of our columns described. So let's give that a try now. I'm going to come back into Python, and I'm going to get my description of all columns. I'll create a new variable called all_description and set this equal to SalaryData.describe. And then in brackets, I will write include equals, and then in quotes, all. If I run all of this code now and open up the all description data frame, you'll notice that I now have a description for program, term, and salary. For program, I have 54 rows, and I have 10 unique values. My most frequent value is mathematics, and it occurs 6 times in the program column. And notice how mean, standard deviation, these are all marked as not a number. Not a number. For salary, take a look at this. We have 54 values, but we have 47 unique values. Our top occurring value is the dash character, and it occurs 7 times in our data. Since mean, standard deviation, min, and our percentiles are all coming back as not a number, this tells us that the salary column has not been read in as a number. So we know that we have 10 unique values in the program column, and we have 47 unique values in the salary column. What if we wanted to get a list of unique values in each of these columns? Well, it turns out Python can do that for us as well. We can use the unique function on a column to either fetch a list of the unique values or print out to screen the unique values. Let's give this a try now. The way we'll do this is by using the data frame variable name dot column name dot unique. So let's get a list of unique programs. I'll create a new variable here called unique programs, and I will set this equal to salary data dot program dot unique. And if I look at my unique programs list, I see that I have applied health sciences, arc, architecture, arts, engineering, environment, mathematics, actuarial science, science, and pharmacy. Already, you may have spotted a data issue, arc and architecture. These are the same program. What about the salary? Let's create another variable called unique salary and get the list of unique salary values. So we'll do unique salary equals salary data dot salary dot unique. If we open up this list, we'll see all of our unique salary values. Now, to you and I, as humans, we can recognize these as numbers, except for this dash, of course. A dash on its own is not a number. We're going to have to do something about that dash. Recall when we read in a CSV file and we get a data frame that Pandas will give us column names based on the first row that occurs inside of our data frame. Program, term, and salary are our column names in this case. What if you wanted to print out all of the column names so that we could use them later? Well, turns out we can print out column names by using the columns attribute on our data frame. So this will give us the list of names of all of our columns in our data frame, and we can use this to make sure that we get the right name when we're referring to our different columns. Let's give that a try. In this case, I'm just going to print out to screen my salary data columns. And you'll see I now have program, term, and salary. Finally, let's return to the D types. Remember how we had 3 columns, program, term, and salary? And program and salary seem to store this magic thing called an object. Well, it turns out in Python we have multiple types. Each of our variables and each of our data frame columns can store a type. And all a type is an indicator that says, what kind of data am I? Am I an integer? Am I a string, otherwise known as text data? Am I a floating point number? Am I something else? In Python, we use the object type as a big bucket that can catch all the other types. Some of the types we've used so far are integers, those are whole numbers, floating points, which are decimal numbers, strings, which is text data, and data frames, which are known as objects. And again, how can we check the type of a variable? We can use the type function. And how can we check the type of what we store in our data frame? Well, we can use the dtypes function. That will give us a list of all the different types in each of our columns.